Good day, everyone. Today, I will present our paper, Computer Science Named Entity Recognition in the Open Research Knowledge Graph. This paper is co-authored by myself and my supervisor, Zoran Auer, and I will be presenting the work. I will begin by offering an introduction to the Open Research Knowledge Graph platform, since our service is developed for it. So the motivation behind the ORKG platform. Currently, scholarly articles are published at an alarming rate of 2.5 million articles per year. A limitation here is that traditional search methods, as a ranked list of documents, can no longer support efficient R&D. While search can pinpoint collections of individual papers of interest, it cannot offer stakeholders a sense of an overview of the field. Therefore, since scholarly knowledge is being produced at an alarming rate, correspondingly, the scholarly knowledge storage and access information technologies need to be rethought and re-engineered to continue to assist the science and industry stakeholders. So at the ORKG, we ask ourselves, what if the global scientific knowledge base would be more than a document repository? In this case, scientific information and knowledge would be fair also for machines. So our overarching R&D question is, since scientific innovations drive progress in companies, industry, and the economy, how can users efficiently discover new knowledge about scholarly innovations in a large mass of literature without a prior search perspective? So the ORKG aims to build a digital library for machine actionable knowledge communicated in scholarly literature as a science-wide knowledge graph. Specifically, its knowledge capture target is scholarly innovations or contributions. Thus, scholarly contributions could be automatically surveyed, they can be automatically visualized and benchmarked. With machine-computable fine-grained scholarly knowledge in the ORKG, the scientist's information access needs via smart information technology, particularly in the face of the rapid publication cycle, is met. So then the question is, how is this machine-computable fine-grained scholarly knowledge captured in the ORKG? This is done through one of two modes, either through domain expert human crowdsourcing or through automated text mining techniques, which now brings us to the focus of this paper. To represent scholarly publications as knowledge graphs, from an information extraction perspective, named entity recognition, or NER, over scholarly publications becomes a vital task, since entities are at the core of knowledge graphs. Hence, our paper proposes an NER service for the computer science domain to be integrated as an ORKG recommendation service. So a typical dilemma with implementing an NER module is deciding the scientific entity extraction targets. In other words, aligned with the ORKG objective of structuring research contributions, the key challenge is how to select only the contribution-centric entities and what would be their types. In this paper, we specifically tackle the scholarly contribution-centric NER problem for computer science. We define contribution-centric CS-NER as involving the identification of a word or a phrase as an entity from CS scholarly articles, either from its title or abstract, or a combination of the two sources, which satisfies one of the following 7 types, namely research problem, solution, resource, language, tool, method, and dataset. So given a title as input, our task is to identify the entities and then type them as one of the 7 types. While all 7 types apply for titles, the abstracts were annotated with only 2 types. So given an abstract snippet, we first identify the relevant named entities and then type them. Our contribution-centric CS-NER definitions were inspired from related work. So a research problem can be seen as the domain, application, or task. A method is the technique or technology and method, while a solution is the focus of the work, and so on. So the plan for the talk is to first introduce our corpus, then discuss the approach and conclude with evaluations. So we start with the corpus. In order to build our CS-NER corpus, we reviewed existing work on scholarly domain named entity recognition. As a first step, all the corpora that did not satisfy the contribution-centric NER objective or which were not restricted to the computer science domain were eliminated. In a second step, NLP-TDMS, CIREX, and ORKG-TDM were based on papers with code as subsets. So instead, we directly queried the full dump of papers with code and released a new version of the corpus in this work as PWC. In a third step, the CL titles corpus originated from the ACL anthology. So in this work, we re-examined its annotations and released the corpus as the ACL corpus. Sci-ERC annotations were then filtered for only the relevant contribution-centric entity type annotations. Thus, only the task entity type for abstracts was retained, which was renamed as the equivalent research problem entity type. Finally, the FTD corpus entity types were renamed as follows: focus, solution, domain, research problem, and technique, method. With this, resultingly, we had two corpora, one, the titles corpus, and the other, the abstracts corpus. This slide shows some of the statistics of the respective corpora. So we see in the titles corpus that solution and research problem entities were predominant, and the abstract corpus, the method entity type, was predominant. So now let's look at our neural approach for building an automated system. The state-of-the-art architecture for sequence labeling includes character sequence representations, word sequence representations, and a CRF inference layer. So inspired from the state-of-the-art architecture, we leveraged it and tested it in 6 ablations of the neural layers, including word CNN and CRF, word LSTM and CRF, word BiLSTM and CRF, and then with the character sequence layers on top of the word sequence representations. So now we move on to the evaluations. The table depicts the results from our various neural architectures. The results were computed in terms of the micro-precision recall and F1 measures on various ablated neural architectures on the titles corpus and then the abstracts corpus. The first row against each neural architecture corresponds to word embeddings that were computed directly from our CS-NER corpus. The second row corresponds to word embeddings that were initialized with pre-trained word embeddings. Specifically, we leveraged GloVe. So the best results from the state-of-the-art architecture, with all the components relying on word embeddings computed on the CS-NER corpus and not from the generic domain GloVe embeddings. We see that the results on the titles corpus are lesser than the results on the abstracts corpus. This is owing to the classification space. Note that the titles corpus handles 7 entity types, which is a relatively more complex space compared to the abstracts corpus, which handles just 2. We refer to the reader to our paper, Computer Science Named Entity Recognition in the ORKG, for detailed experimental analysis and discussion. So with this, we've seen the evaluations. We started by trying to develop a service for the Open Research Knowledge Graph platform. So let's see what it actually looks like in practice. So the service is then integrated per the screenshot in the ORKG platform, where the highlighted box corresponds to automatically extracted annotations from the paper title and abstract. And thus, a domain expert can simply click these entities and add them to their contribution description in the ORKG. So as a conclusion, we have seen that contribution-centric CS-NER achieves performances above 75% on a corpus of paper titles and above 80% on a corpus of paper abstracts. Our corpus and code base are all publicly available, and the links are also available in our paper. Thank you for your attention, and now I'm happy to take questions.